Okay, so for this, we are going to walk through proof by cases, and then we're going to do two different proof methods in addition to that. So we've got three proof methods we're going to go through today: proof by cases, proof by contrapositive, and proof using the contradiction. So proof by cases, we actually did one already. We did this the other day. We proved that every integer is either even or odd using the quotient remainder theorem and deciding if we use this divisor of 2, then our remainder has to be 0 or 1. This gives us options. It has to be this or this, and that breaks us into cases where case 1, we let it be 1, case 2, we let it be the other one, show it works in either case, and then we've done the proof. So we're going to do something similar to that today with this, given any two consecutive integers, one is even and the other is odd. So I'm going to do some scratch work and talk about sort of what that means. Is that straight? Yes, okay. So consecutive integers, that means like 2 and 3 or 5 and 6. So one right after the other. So we're going to let A and B are consecutive integers. We're going to assume that B is A plus 1. You can do this the other way too, but this is fine. And then what we're going to do is, okay, well, we just proved that every integer is either even or odd. So we're going to let A be even or odd, and that's going to break us into our two cases. So once we have A is even, we'll get that B is odd. And when we have that A is odd, we'll get that B is even, making any two consecutive integers where one is even and one is odd. So let's write a proof. We are going to let A and B be consecutive integers. Assume that B is the bigger one. So assume that B is equal to A plus 1. Now, A is either even or odd. We proceed with cases. This is just a way to organize your proofs when you have stuff like this. So case 1, we're going to assume that A is even. So then A is equal to 2k for some integer k. Notice maybe B is equal to A plus 1, so B is 2k plus 1. And then since k is an integer, B is odd. Case 2, we are going to assume A is odd. Then A is going to equal 2L plus 1 for some integer L. Okay, then B is equal to A plus 1, which is going to be 2k plus 1 plus, oh, that's an L now, sorry. So this is 2L plus 2. So we're going at 2 times L plus 1. Oops, I'm running out of space here. Since L plus 1 is an integer, B is even. Thus, in either case, one is even and the other is odd. For consecutive integers A and B. Okay, so the proof is not that different than what we have been doing. It's just that you like walk yourself while you're chasing this rabbit, you sort of like move yourself into this place where you have choices. Those two choices give you the cases. Okay, this one is less obvious. I'm going to shrink this down a little bit so it can fit in my space. I have the ability to do that. I'm sorry that you don't and that I didn't give enough space for that. All right, so this one we have a and b are non-zero integers. A divides b, b divides a. Then either a equals b or a equals negative b. So if we do scratch work here, whoa, we get to assume that a divides b and that b divides, whoa, and that b divides a. If a divides b, then b is equal to a times k. If b divides a, then a is equal to b times l. This is for k and l and z. This is from the definition of divides. So a divides b means that b is a times k. B divides a means that a is b times l. So we're going to look at this. Why not like this? So a is equal to b times l. B is ak. So you're looking at this. So a is equal to a times kl. Well, kl has to equal 1 for that to work. Now, the only way that that can happen is that k and l are both 1, or k and l are both negative 1. That's going to give us our two cases up here. So we're going to write proof now. Let a and b be non-zero integers such that a divides b and b divides a. By definition, b is equal to a times k and a is equal to b times l for some integers k and l. Notice a equals b times l, which is equal to a times k times l, which is a times kl. Now, kl equals 1, so k equals l equals 1, or k equals l equals negative 1. We proceed with cases. Case 1. Let k equal l equal 1. Then a equals b times l, which is b times 1, which is b. So a equals b. Sorry, I was trying to figure out a way to organize this differently. A equals b times l. Clearly, a equals b. We'll just go with that. Case 2. Let k equal l equal negative 1. Then a equals b times l gives a equals negative b. Thus, when a divides b and b divides a, we have either a equals b or a equals negative b. Again, the proof is not that different than what we've been doing. It's just that you like walk yourself into a place where you have choices. And you sort of organize those choices into two mini proofs, basically. Okay, but now our second proof method for this video is the proving using the contrapositive. This is an indirect argument. So everything we've done to this point are their direct arguments. You assume P, you show Q follows. This is a different method. So the implication P implies Q is equivalent to the contrapositive, right? So sometimes if you're trying to prove that P implies Q, it makes sense to assume the not Q and show that not P follows. This is particularly true in some of these that we're going to do where it's like you're stuck if you assume the P part. But if you could assume not Q, then you're not stuck. So when you're going to write this proof like this, you are going to say it. So to prove this, we're going to prove using the contrapositive. Assume not Q. And then you'll go forward and say, okay, then not P, therefore, and then put the original statement back at the end. So let's go through that. And let's talk about why this makes sense here. So on this one, we have if n squared is even, then n is even, right? Well, n squared being equal to 2k is not helpful for me to get n by itself. I would need to take a square root. We don't know how to do square roots yet. So like this, I can't do. If instead I could assume that n was not even and show that n squared is not even, I'm proving the same thing because those statements are equivalent. So this is n squared even implies n is even. This would be equivalent to saying n not even or n odd implies that n squared is not even or is odd. I don't know if I said that right just a second ago, but okay. So this how you do proof by contrapositive. It's kind of cool that, we have accepted the fact that the contrapositive is equivalent, but accepting that proving the contrapositive proves the original is kind of weird. But so we are going to do using the contrapositive. I'm probably just going to write this then. Contrap. If n is if n is odd, then n squared is odd. I don't know that I need this here. We'll move this over. Oops, I lost half of it. Okay, whatever. Let's just get rid of it. I'll write it over here. Contrap. N odd implies that n squared is odd. Proof. We will prove, this is the statement here. We will prove using the contrapositive. Assume n is odd. Then n is equal to 2k plus 1 for some integer k. Notice n squared is 2k plus 1 squared, which is 4k squared plus 4k plus 1, which is 2 times 2k squared plus 2k plus 1. Since that thing is an integer, 2k squared plus 2k is an integer, n squared is odd. So by contra, this is a weird word, position, if n squared is even, then n is even. So I've like restated the thing I was actually proving there at the end for the like conclusion bit. So proof by contrapositive, assume not this, show not this, and then say, because we've done this, we know that this way is true. All right, another example. N is an integer and n cubed plus 5 is odd. Then n is even. Again, to prove this directly, we would assume n cubed plus 5 is equal to 2 times an integer plus 1. I've got to get n by itself. So I got to subtract 5 from both sides. Okay, well, that's, whatever. I can do that. But then I've got to cube root stuff. I don't know how to cube root anything, so we can't do that. It doesn't make sense to try to prove this directly, so we're going to prove it indirectly using the contraposition. I'm going to just start writing a proof, and we'll use scratchwork if we need to. So the proof, oh gosh, I don't think I can cube this thing. Hold on, we'll give it a shot. We will prove using the contrapositive. Assume n, oh no, assume n is odd. Then n is equal to 2k plus 1 for some integer k. Consider n cubed plus 5. Yikes. I should be able to do this well, and I know that. 2k plus 1 times 4k squared plus 4k plus 1. There's a trick. I know there's a trick, but I don't remember the method. So we're just going to have to do this by hand, and that's okay. That's 8k cubed first, and then plus 8k squared plus 2k plus 4k squared plus 4k plus 1 plus 5. I think I did that. We got 8k cubed, 12k squared. Ooh. Does that feel right? Maybe. 8k cubed, 12k squared, 6k, and 6. Okay. We're going to take a 2 out of all of this stuff. So we're looking at 4k cubed plus, 12 divided by 2 is 6. That's a 3. That's a 3. So since that thing, 4k cubed plus 6k squared plus 3k plus 3 is an integer, n cubed plus 5 is even. So by contraposition, maybe say this is even when n is odd. So by contraposition, if n cubed plus 5 is odd, then n is even. Okay, so again, it makes sense that you would need to start over here, but you got to do the opposite. So you're going to assume not this part and then show not that part. I maybe am not going to do contradiction today. We'll save that. Prove that for all real numbers x, if x is irrational, then 1 over x is irrational. We don't know anything about irrational, so doing this directly is hard. Like that, so what we are going to do is we will assume 1 over x is rational and show that x is rational. So not this implies not this. Proof, we are going to we will prove using the contrapositive. Assume that 1 over x is rational. Then 1 over x equals a over b for some integers a and b with b not equal to 0. I'm going to say something like this. Since 1 over x is in the rational, so that's the big Q, x can't be 0. Okay. So since 1 over x equals a over b, we have multiply both sides by x. I want to make sure we can flip this without doing any sort of division. We get 1 is equal to ax over b multiplied by b divided by, oh, we don't know how to divide by a. Yeah, we can divide, we just don't know that it's an integer. That's okay. But it is an integer. The a value is an integer, so we're good. And I know that I can multiply by x. I know that a isn't 0 because x isn't 0. I don't know that we know that. Okay. So we get b over a is equal to x, just the reciprocal there. Now, a and b are integers. And a cannot be 0 since 1 over x can't equal 0 anywhere. Thus, x is rational. That is convincing yourself that x can't be 0 there makes that work. Oh, I have to do the thingy. This works, sorry. 1 over x can't be 0 anywhere. That means x can't be 0, but it also means that a can't be 0 because 1 over x can never give you 0, and if a was 0, then it would have to. There's no value for b or x that can make that work. Okay, so by contraposition, if x is irrational, then 1 over x is irrational. All right, just one more and then we can be done for today. This one's fun. If p divides into the k, then p divides n. Starting with the bigger thing is weird, so we're going to start with this thing. Let's just do some scratch work for this one. So we're going to assume p does not divide n. Show p does not divide n to the k. So n is equal to some prime factorization, p1, p2, all the way to pn, where p doesn't divide any of those p sub i's. Well, it's a lot of notation happening. This is its prime factorization, which we can do because of the fundamental theorem of arithmetic. The fact that p does not divide n means that none of these p's is equal to p sub I. I guess I can put equal, not equal to this. Our p that we're talking about isn't any of those p's, those prime factors. These should probably have exponents, huh? Call these A1, A2, AN for these exponents. The prime factorization is, the powers of the primes. So, all right. And then if we were to raise that to a power of k, we'd raise this whole thing to a power of k, which would give us P1, A1k, P2, A2k, all the way to Pn, ANk. So since P isn't any of those P sub i's, this gives us that P doesn't divide P sub I for any of those. And the same thing too, P will not divide P sub I to the K. Thus, P does not divide into the K. So this one, the proof is messy, but, well, this is not a proof either. Scratch work is messy here, but we know we can write n as the powers of primes multiplied together from the fundamental theorem of arithmetic. Say this is, I don't know, 35, right? Then we can write that as 5 to the first times 7 to the first. We're picking some prime that it isn't either one of those. So it's not going to divide either one of those raised to a power that's bigger, because the primes are not going to change. It's just going to be more copies of them. So it makes sense that if P divides into the K, then P has to divide it in, because it's a prime. I think that makes sense. So in class on Monday, we'll start contradiction stuff, and we'll get through this stuff. This is fun. Yeah. Okay, that was longer than I intended for it to be, but hopefully it was helpful. Let me know if you guys need any help, and I will see you soon.